Okay, this is a screencast on the Doppler effect. What is the Doppler effect? Well, it's the apparent change in frequency of a wave, so a light wave, sound wave, doesn't matter. The apparent change in frequency of a wave due to the relative motion between the source of the wave and the observer. What does that mean? Well, it means that the frequency of the wave seems to change if the source of the sound, source of the wave, is moving, or if the observer is moving closer or further away from the source of the sound. So the best example of this is if a car is driving towards you. So when a car is driving towards you, it seems to have a high pitch, or in other words, a high frequency. But as it pulls up alongside you and prepares to drive past you, the moment that it's sort of parallel with you, you'll notice the pitch decreasing. And then as the car passes you by and drives away from you, you'll notice that the pitch decreases further. So the pitch, or in other words the frequency, is initially high as the source of the sound, the car's engine, is moving towards you, and then it's at some lower frequency as the car is moving away from you. But so what's the real frequency? And why do we experience this change in frequency? Well, if we imagine some point source here, and this is going to emit a wave, and that wave is going to spread it in all directions, in this direction, and this direction, and so on. So it's going to emit a wavefront, right? And if we think about this wavefront spreading out over time, and if the source was stationary, then it would continue to emit new wavefronts over time. And when we're speaking about time and waves, it's useful to talk about time periods. So the period of a wave is the time taken for one complete cycle, or in other words, it's the time taken from when this wavefront was first emitted from the source and when a new wavefront will be emitted from this source. So let's consider that whatever time it took for this wavefront to reach this point from its source here was one time period, t. Then that means that the distance it traveled in that time would be one cycle, or in other words, one full wavelength, lambda. But because we're talking about the Doppler effect, we're talking about not a stationary source, but a moving source. And so the easiest way to explain this is to go back in time. And we can think about the position of the source of the sound wave at various points in time, in the past. And what happened to the sound waves and the wavefronts that were produced in the past. And when I say we're going to go back in time, we're going to go back in time by, well, first of all, one time period. So if I go back in time by one time period, then the source of the wave, it must have been over here somewhere, because I said the source is traveling from left to right. So the source is going to be over here. And let's say that it's here at this point, this red dot. Well, if this is a time, one time period in the past, then whatever wave was emitted from this point at that time will have traveled one additional wavelength than this wavefront. So the wavefront that was emitted by the source, by the car say, when it was at this position, will have traveled two full wavelengths by the time that this wavefront emitted from this point has traveled one wavelength. Why? Because, as I said, it's one time period ago, so the distance that it traveled from here to here took one time period, which means whatever wave was emitted from this point will have traveled one extra wavelength of distance compared to any wave emitted from this point. Okay, so let's draw that wave in. It'll be like this, so it'll have twice the radius of the black circle. And so this distance here will be 2 lambda. And then if I go back in time by another time period, and I say this point here, as I've mentioned before, a wavefront will travel one additional wavelength for each time period, so that will have traveled a distance of 3 lambda in that time. And it's important to notice that this point here is the center of this green circle, just as this point is the center of this red circle, and this point is the center of this black circle. And that's because, as I said, if we traveled into the past, when the car, or whatever it is that's emitting the sound, is at this point, then the wave will spread out from this point in all directions, which is why we get this circular wavefront. But even if the car moves from here to here, the sound wave or the wavefront that was emitted when the car was here will continue to move out from this point. And so as the car is moving from left to right, it's emitting these sound waves. And so when you think about that, if you think about this black wavefront, and by the time that wavefront, which was emitted from here, has traveled a distance of one full wavelength lambda, the source of that wave will have continued moving. So it won't be here anymore, it'll be over here somewhere. It'll have traveled some distance in that time period, okay? Because it will have taken one time period for the wave from being emitted from this point to have reached one full wavelength. So the source is actually over here somewhere. And so if you were an observer, and you're standing over here, what you would notice is that the wavelengths seem to bunch together here. So this is our actual wavelength, but if you're standing here, then you notice this different wavelength. You notice what we call this apparent wavelength here. And we're going to call that lambda prime, the apparent wavelength. Because as these waves travel and reach you, your ear will notice not this wavelength, but it will notice this wavelength. Now, the speed of the wave is remaining the same. And remember, our equation for the velocity of a wave is equal to lambda times f. Except in this case, you're not experiencing lambda, you're experiencing lambda prime. And lambda prime is some value less than lambda, so the wavelength seems to have decreased. But if the velocity has stayed the same, that means that if lambda has decreased, then f must increase by some amount so that v stays the same. So we're going to call this f prime. And that's the apparent frequency of the wave, and that's why you experience that change in frequency or pitch as the object or the source, the car or whatever it is, moves towards you. Now if you were standing on the other side, if you were standing over here, then you'd experience a different wavelength again. You'd experience this apparent wavelength, which is larger than the actual wavelength lambda, which is why as the object moves away from you, so if you were standing over here and the car is moving from left to right, as it moves away from you, the frequency seems to decrease. So, as I mentioned earlier, the Doppler effect occurs either because of a movement of the source or a movement of the observer. So the first example we're going to talk about is a moving source. So if we imagine some source of a sound, again we can take a car engine as a good example, and this point here is our source of the sound at some moment in time, and it emits a wavefront. Well, after a time period t, that wavefront will have travelled the distance of lambda, right? But also in that time period, the source has moved to some new position. It's moved to this position here. And so if this is a time period t, then this source is just about to emit a new wavefront, because that's the definition of the time period, is the time taken for one complete cycle. So this, in a time period t, that this source moved from here to here, it'll be just about to emit a new wavefront or a new crest. Then for an observer standing over here, they will experience this wavelength that we mentioned before, lambda prime. And it's useful to sort of define the distance that the source, the car in this case, travelled in that time. Well, as I already mentioned, the time that it took was t, one time period. And we know already that speed is equal to us. us for speed of the source. But speed equals to distance over time. Therefore we can say that us is equal to d, the distance, divided by the time which is one time period. So we can define the distance d as us times t, the time period. Now this distance here is equal to this distance here, right? It's just the radius of that circle. So in other words, this distance is equal to this plus this. Or we can say lambda is equal to d, which is really us times t, plus lambda prime. But by rearranging our speed equation for a wave, we can say lambda is equal to v over f, and we also know that the time period t is equal to 1 over f, and lambda prime is going to equal to v divided by not f but f prime. Therefore, I can rewrite this equation as Vf, substitute for lambda, us over f, I've just substituted t for 1 over f, plus v over f prime. So I've substituted lambda prime for v over f prime. Now what I basically want is to get f prime by itself. So I want a way to calculate f prime. I want f prime equals to something. So I'm just going to rearrange this equation. I'm going to skip a couple of steps. So I end up with an equation where I have something with f prime in it by itself. And if I cross multiply, I get f prime on v minus us is equal to v times f. Therefore f prime equals to f times v over v minus us. Sorry, skipping ahead of myself a little bit. So I get f prime is equal to f times v over v minus us. Now this only works when the source is moving toward the observer. So what if I was standing on the opposite side over here and the source was moving away from me? Well, now the source is over here, remember, it's about to emit a new wavefront, and this other wavefront has reached this point here. So this distance here will be the apparent wavelength, the wavelength that I experience. And so we can say that this distance lambda is equal to lambda prime minus d, or in other words, lambda prime is equal to, lambda is equal to lambda prime minus us times t. And once again, I want to substitute my lambdas for v over f and my lambda prime for v over f prime, because I want to speak about the frequency. And if I do all that and summarize it again so that I get f prime by itself, I can say, therefore, f prime is equal to f times v over v plus us. And that's when the source is moving away from the observer. So I can combine those two formulas and I can say f prime is equal to f times v over v plus or minus us. I'm going to put that in a box. And that's for any moving source. So you have to be able to decide whether to use v plus us or v minus us. And basically, if you think about it this way, if the source is moving towards you, then f prime is going to be higher than f. So when is f prime higher than f? Or in other words, when is f prime sort of at a maximum? You want f prime to be bigger. So when is f prime bigger? Well, it's bigger when the denominator is smaller. Or in other words, when the denominator is v minus us. So v minus us is going to be bigger than v plus us. And the opposite is also true. So if the source is moving away from the observer, then f prime is going to be smaller than f. So you want f prime to be as small as possible. So when is f prime as small as possible? Well, it's when the denominator is as big as possible. So in that case, it'll be v plus us. So depending on the situation, you'll use either one of these forms of that formula. What about for a moving observer? Well, the observer is moving, we've still got some source that's emitting some sound, but in this case it's stationary. So as it emits its concurrent wave fronts, it'll look like this. So because the source is stationary, we don't see any apparent change in wavelength. The wave fronts just spread out from that point, and they're spreading out in all directions. And the waves are traveling with a velocity v. So if they're traveling, let's say they're traveling towards some observer over here, but the observer is also traveling towards the waves with a velocity uo. So we use o in this case for observer. Then for the observer experiencing these waves traveling towards them, he doesn't, or she doesn't, notice the waves traveling with velocity v. They will notice some other velocity, some apparent velocity. And think about it this way: if you were driving down the highway and you were driving at 100 kilometers per hour, and the car in front of you was traveling at 120 kilometers per hour, then the relative velocity of that car to you would be 20 kilometers per hour. You wouldn't see that car as, or you wouldn't notice that car was traveling at 120 kilometers an hour. Because you're traveling at 100 kilometers an hour, you only notice the car, or it seems to you that the car is traveling away from you at 120 kilometers an hour. Or if you imagine a car driving towards you, if you were traveling forward at 100 kilometers per hour and a car was traveling towards you at 100 kilometers per hour, then if you imagine that your car was stationary, it would seem that the other car was traveling towards you at 200 kilometers per hour. That would be the relative velocity of that car. And that should be somewhat familiar to you from vectors when we did the velocity of vector A with respect to B and so on. So although the waves are traveling at some velocity v, we're going to say but the relative velocity, and we're going to call that v prime, in other words the apparent velocity of the wave to the observer, is v plus uo. So we can say v prime is equal to v plus uo, and it's the frequency I'm interested in calculating, so I'm going to substitute v prime for lambda times f prime. Why is it lambda and not lambda prime? Well, because as I said, in this case there is no apparent change in the wavelength. If we look at our example here, the source is stationary, so there's no apparent change in wavelength. So v prime is equal to lambda times f prime, and we can substitute v for lambda times f plus uo. Now I want to get rid of these lambdas as well, because again I really just want to talk about frequency. So by rearranging our wave equation, we know that lambda is equal to v over f, so I'm going to substitute lambda for v over f in both cases. The f's cancel in this case, and I'm left with v times f prime all over f is equal to v plus uo. And if I rearrange that to get f prime by itself, I get that f prime is equal to f times v plus uo all over v. And that's for an observer moving toward a source. So just like I did before, I can do that again. So I'll say similarly for an observer moving away from a source, and without going through all the calculations again, I can say f prime is equal to f times v minus uo all over v. And therefore that's for an observer moving away from a source. So I can summarize both formulas as f prime is equal to v plus or minus uo over v for any moving observer. I'll put a box around that. Now this works for any type of wave, but when we deal with light, we have to talk about a couple of different formulas. So our equation for calculating f prime for a moving source does still work for light, but if we're talking about light, then v in this case equals to c, the speed of light. So we rewrite our equation, and in this case we substitute v for c. And here the c's are going to cancel, so I'm just going to say I'm going to rewrite this as f times 1 plus or minus c over us. And for reasons that I'm going to explain in a second, I want to basically invert everything that's inside these brackets. So I can do that by multiplying everything inside the brackets to the power of minus 1. And if I do that, then I can say f prime is equal to f on 1 plus or minus us over c all to the power of minus 1. And if I consider my equation for a moving source, then I get f prime is equal to f times v plus or minus uo all over v, and that all equals to the following when I substitute v for c. And again, the c's cancel and I'm left with f prime is equal to f times 1 plus or minus uo over c. Now, because of some complicated mathematics and of this thing called the binomial theorem, which you may study in maths but that we don't need to know in detail for physics, so I'm going to skip that and I'm just going to say because of the binomial theorem, both formulae reduce to f prime is equal to f times 1 plus or minus 1 on u over c. And if you're interested, you can look up the maths on that, but basically what it means is because of this binomial theorem, if we have f prime is equal to f on 1 plus or minus us over c to the power of minus 1, and we also have that f prime is equal to f times 1 plus or minus uo over c to the power of 1, then we can reduce both formulae down to this single form. And then if I multiply that out, I get f prime is equal to f plus or minus f times u over c. And therefore, I can subtract f from both sides. So if I say f prime minus f is going to equal to plus or minus fu over c. Now saying f prime minus f is just really another way of saying delta f, the difference between f and f prime. So that's going to equal to plus or minus f times u over c. And then if I divide delta f by f, I get delta f divided by f is equal to plus or minus u over c. Now, u is the speed of the source or the speed of the observer. But it really amounts to the same thing. It amounts to the relative velocity between the source and the observer. Okay, so the IB calls u v. Now this can be kind of confusing because usually when we're talking about v, we're talking about the velocity of the wave. Okay, but in this case, v is the relative velocity between the source and the observer. So therefore, if I replace u with v, I can say delta f divided by f is equal to v over c, and I'll put that in the box. And you might notice that I lost this plus or minus here. Okay, now that's basically because what I'm really interested in is delta f, and I can decide later on whether delta f is positive or negative, or in other words, whether delta f, the difference between f and f prime, is going to be subtracted from f or added to f. What do I mean by that? Well, let's say I've got some source emitting a sound wave, and that sound wave is being emitted at, I don't know, 200 megahertz. Okay, and I know that f prime is 20 megahertz. Or sorry, I know that delta f, the difference between f and f prime, is 20 megahertz. So I've got a sound wave, which I know the frequency is 200 megahertz, and delta f is 20 megahertz. But does that mean that f prime is 220 megahertz or is it 180 megahertz? In other words, is delta f positive or negative? Should I add delta f to find f prime or take it away? Well, that will depend on the relative velocity v between the source and the observer, or in other words, is the observer moving away from the source? In which case the apparent frequency f prime is going to be some value lower than the frequency. So I'm going to subtract delta f from f to find f prime. But if the relative motion between the observer and the source is bringing those two together, then f prime is going to be increased. It's going to be some value higher than f. So I'm going to add delta f. So I don't need the plus or minus here. I can use this formula, and depending on the situation, I can decide whether to add delta f to my frequency value or to subtract it. And when you do some IB practice questions, that will make more sense. So I'm just going to add this little footnote here, and I'm going to say v is not speed of the wave. And that's important to remember for this equation. Now I'm going to do a little bit more, because sometimes we'll want to speak about the wavelength of, or the apparent wavelength of the wave, or the change in wavelength of the wave due to the relative motion between the source and the observer. So for light questions, sometimes you might be asked if an instrument observes light at this wavelength, the apparent wavelength, but we know that the source is moving away from the observer, then calculate the actual wavelength. And so for that, I'm going to use my speed equation, c is equal to lambda times f, and I'm going to rearrange that as lambda equals to v divided by f. And the relative velocity, remember from our previous slide, is v plus c. So the velocity of the observer or the source plus the speed of the actual wave. And if it's a light wave, then that speed will be c. So if, as I mentioned here, lambda is equal to v over f, and therefore I can say lambda prime is going to equal to not v over f, but v plus c over f. Remember, the apparent speed of the wave is going to be v plus c. But f equals to c divided by lambda. That's just another rearrangement of this equation. So therefore lambda prime is equal to v plus c divided by c over lambda. And that comes out as v plus c times lambda over c. Now c over c here is going to give me 1, and v over c is just v over c. So I can rearrange this as lambda prime is equal to 1 plus v over c all multiplied by lambda. And if I multiply that out, I get that lambda prime is equal to lambda plus v times lambda over c. And then I'm going to subtract lambda from both sides, so I'll end up with lambda prime minus lambda is equal to v times lambda over c, and therefore lambda prime minus lambda is just delta lambda. And if I divide by lambda, I get delta lambda over lambda is equal to v over c. And if you look to the left, you'll notice that v over c is also equal to delta f over f. Therefore I can say that delta f over f is equal to delta lambda over lambda is equal to v over c. And I'm going to put a double box around this formula. This is our final formula that we can use. And depending on whether the question asks you to calculate the frequency, for example, giving you the wavelength, or whether it gives you the relative velocity between the source and the observer and asks you to calculate the change in wavelength, you can use different forms of this equation depending on the type of question that you're asked and the information that you're given. But this equation sums up how we can use the Doppler effect for light. And questions that come up a lot tend to be to do with stars maybe in other solar systems moving away from the Earth and calculating the wavelength or the frequency of the light as it's observed by some piece of equipment on Earth. And so that'll depend on whether the star is moving away from or towards Earth and at what velocity. And in general, because the Earth is expanding, stars are moving away from us. And that gives rise to this phenomenon that you'll see coming up in some questions called redshift. And what redshift basically means is, well, if a star is moving away from planet Earth, then as the light travels to Earth and is observed at Earth, it won't be observed at the frequency at which it was emitted. It'll be observed at some frequency f prime, right? And if the source, the star, is moving away from Earth, then it'll be at some frequency less than the actual frequency. And because this is visible light, we say that the light is moving towards the red end of the spectrum. So red has the lowest frequency of visible light. So if the frequency is reducing, it's moving towards the red side of the spectrum. It's getting redder as such. And we call that red shift. Now, if the relative motion between the source, let's say a star for example, and the Earth is bringing those two bodies closer together, then the apparent frequency f prime will be increased, and therefore we call that blue shift. So blue light is at the other end of the spectrum as the highest frequency of visible light. And so whether you get blue shift or red shift tells you whether the star that you're observing is moving away from or towards the Earth. Okay, so that is your screencast on the Doppler effect.